What's up guys, it's Sean here, and today on The Computer Scientist we're going to be exploring some of the deep learning puzzles on OpenAI Gym as well as code up an agent to play them. OpenAI Gym is pretty much like a gym for testing out different reinforcement learning algorithms on various simulated environments with the overall goal of maximizing the reward from interacting with that environment. So let's start by checking out the homepage for OpenAI Gym. There are different environments to try out, ranging from the simple grid world type environments rendered on the command line to ones with more complex dynamics, and then the more difficult environments with many complex variables. So today we'll mainly be looking at the classic control environments. First we need to install Gym with pip install Gym, which I've done already, and then we just import Gym. So next we will create an instance of the environment we want to play through. So let's have a look at the classic Cartpole environment. So we'll then save the name as a variable and then call gym.make, passing in that name. So env is now our handle for interacting with the environment, which we can use to simulate a random playthrough. Now we first reset the environment state with env.reset and then iterate over a number of time steps, where at each time step we get a random action by calling env.actionspace.sample and then apply that action to the environment by passing it to env.step. Finally, we call env.render to display the graphics. Okay, so if we want to design our own agent to play optimally in this environment, we will need to start by understanding more about the interface of the environment object. So let's check out the wiki for the Cartpole environment on the GitHub page. So we see that the environment has an observation table, which is essentially the current state of the environment, and this specifies the possible values for the cart's position along the line, its velocity, and also the angle and the angular velocity of the pole. We then have an action table which tells us what actions correspond to each action index. So 0 is push the cart left and 1 is push it right. We can actually access all of this information from our env object. So looking at the attributes of this object, we can see an observation space, and when we print it, it comes up as box 4. And this means that it has 4 values, each within a continuous range. Then if we look at the action space attribute, we see that it is a discrete 2, which means that it has 2 discrete action index values, normally which start from 0 and go up to the number of different actions available. So now let's create an agent class that uses this information from the environment to make custom actions. So within our constructor, we can save the number of actions available as env.actionspace.n and also print it to see what this is. Then we can define a method for choosing an action from the available actions. So in this case of a discrete action space, this would just be an integer from 0 to the action size exclusive. So for now, we will just return a random integer in that range. Then we just need to create an agent object and call its getAction method to get an action for the environment. Now, what if we wanted to define our own simple policy for choosing an action based on the current state of the environment, or the cartpole? So if we think about how we would balance the cartpole, we would push the cart in the direction that the pole is leaning to try and counteract its tilting. So looking at the observation table, we see that the information about the pole angle is at index 2 of the observation space. So that means we need to pass the current state to our agent when choosing an action for the next time step. So it turns out env.reset actually returns the initial state, and then env.step returns a tuple containing the next state, a reward for the last time step, whether or not the episode reached a terminal state, and finally some additional info. So having a terminal state essentially provides a finite ending point for each episode, so it doesn't go on forever. And the conditions for an episode terminating are included in the wiki as well. So now that we have the state, we can pass that to our agent, and then our agent can access the pole angle at index 2 of the state and push the card to the left if the angle is negative, otherwise push it to the right. So now you have an idea of how to set up a basic interface for interacting with an environment on OpenAI Gym. In the upcoming episodes, we'll be building on this setup to eventually train an agent to make the optimal moves for an environment. So make sure you subscribe if you want to stay up to date with those. Anyways, thank you so much for watching this video. If you found it helpful, be sure to give it a like, and I'll see you next time on The Computer Scientist. Bye!